So we are streaming live, Nitin.
Okay, sir.
You're the host, Nitin. You can share your screen and maybe get started in 1-2 minutes. Yeah,
Okay.
all yours.
Okay. Okay, good evening. We'll start. Today we are doing electricity, basic definitions. Okay, so we have electric charge. The charge is basically we are talking about is Q. Okay, when we are talking about charge is basically Q. Now Q is the unit for this is coulombs. Coulombs. The first thing which we come into the picture is basically we use charge that was to define current. When I'm trying to define current, I'd say what there's rate of flow of charge is basically current. Rate of flow of charge. A rate of flow of charge basically in terms of current, if we are talking about big charge, we are talking about electricity, that is charge on electron. Rate of flow of charge is this. Okay. Now the first formula relating to this is what I have I is equal to Q upon T. You write it as Q upon T, or you write the I is equal to change in Q upon change in time. Okay, change in Q into change in time. And now see, this is basically we are talking about, this gives you instantaneous current. Okay, this gives you instantaneous current. The normal formula where we have to find out I average. So finding out I average, what formula we use? We will use delta Q upon delta T. That is change in the value of time charge by changing the value of time. And this is basically what this is. I'm differentiating Q in the form of with respect to time. This is differentiation of Q with respect to time. This is the first thing where we are talking about the rate of flow of charge. Next thing, see now we're moving to the basic properties of charge. If you're talking about property of charge, first thing what we write, it's a scalar quantity. If I'm talking about charge, charge is a scalar quantity. First point. I'm talking about second point, it is normally what we can add it, normally additive in nature. Normally how we add like +2, -2. So we just add them without talking about any direction. Like I have some +2 Coulomb, -4 Coulomb, 6. Like this, normally we just add it up. We don't have any thing to be used with, because it's scalar quantity, we don't have to use any vector methods in that. What is important in terms of properties is conservation of charge is there, but the most important property for that is quantization of charge. So we say what is quantization, that property. What is quantization of charges? Q can be written is equal to integral multiple of the fundamental charge E, where E is basically what? It is 1.6 into 10 to -19 Coulomb. This is basically charge on an electron. So what is N? N is number of electron, and that is what. So that's what we write it as, that N into E is equal to your quantization of charge. We say is a charge an integral multiple of the fundamental charge E, whose value is 1.6 into 10 to -19 Coulomb. You can have exceptions. People say that you have exceptions when we are talking about quantization of charge. It is Cox. Cox basically you write it in the terms like you have charges in there. You can see that it is written in the form of 2 by 3e or 1 by 3e plus, sometimes plus, sometimes minus. So what we say is this is still follows quantization of charge, but here what difference will be there? N still remains. Now here n value is what? N value will 1, 2 like this. So here also in case of quarks also the value of n will still remain as 1, 2, 3. Only things what E will change here as E upon 3. So still we can say that quarks when it still follows the quantization of charge. So quantization of charge is nothing but Q is equal to Ne, which is where n is number of electrons and E is the fundamental charge. Okay. Next we have method of friction. Method of charging. The method of charging first is friction, normally by rubbing. The example for that is mostly in common example is you tear a few pieces of paper, you rub your scale against the hair, and then you try to take it nearer to those teared piece of paper. This will get attracted towards the ruler. That is friction, normally where we'll have what charge will be transferred. One will gain electron, other will lose electron. Because of that, one will behave like as cation, other will behave as anion, and because of that, charging will occur. So this is what is friction. Friction is obviously not that much important. What is important for you is conduction and induction, where induction is most important. When we're talking about conduction and induction, we just see the major difference. See, if I'm talking about conduction, so say in case of conduction, what happened? We took two bodies, 1, 2. In this one is charged. This is charged body, and this is uncharged body. It is charged and one is uncharged. So now see if I'm assuming that it is having positive charge, which is uniformly distributed on this 1, 2, 3, 4, 5, 6. And now this is uncharged. So now this was having plus Q charge. What happened when this is brought in contact? These two came in contact and then it was separated again. So what was observed that this charge gets evenly distributed with this two. So what will happen? This also will get plus Q charge. This also will get plus Q charge. But now the magnitude will become what? It will become Q by 2 here, and here also it will become Q by 2. So what is conduction here is when you do what you bring an uncharged body in contact of a charged body, and when you separate them, the charge gets evenly distributed between both the bodies. What is supposed to be observed that here you get the same charge. Okay, the charges will not be different. The same if you brought positive charge near to an uncharged body, this will also get positive charge. If you're bringing a negative charge body, this will also getting a negative charge. Okay. Next thing, when I'm talking about induction, what happens in induction is, for example, we have induction again. Also, same thing is there. We have a charged body and we have an uncharged body. So what happens? We don't bring them in contact. What we do is we just try to bring them nearer to each other. So if this is getting positive charge, if this is having positive charge. So what happens? All the positive charge of this gets accumulated on this side of the sphere. So because of that, what will happen? This particular side of this uncharged sphere will start getting a negative charge. And because this is getting negative charge, this end starts getting positive charge to maintain the electrical neutrality. What we do earthing of this. So when you separate them again, then what will happen is this will have the positive charge and this will get negative charge. And what will happen here is, so you can see that what is the difference here? It was you were bringing plus Q, it was getting plus Q. Here you were getting plus Q, nearer they were not in the contact. This came plus and minus Q. And now what will be here? Here the magnitude stays same. Magnitude of charge doesn't change. If it is Q, this also will stay Q. If this is Q by 2, this will become Q by 2. So that's also a major difference between conduction and induction, where induction is very important because we can use it. If I want a negative charge here, I can bring positive charge nearer to it. If I want a negative charge, a positive charge, I have to bring a negative charge. That's all. Okay. In case of induction, normally the charge also is useful. It will be increased. Okay. So we have a formula here for induction where Q dash is the new charge. this is the initial charge 1 minus 1 upon k, where k is what? Dielectric constant. Okay, k is what? It's a dielectric constant. So you can see that the sign is negative. If here it is negative, this will become positive. If here it is positive, this will become negative. That is what is. And when in the case of metals, when I'm talking about k, in case of metals or conductors, k value will become infinity. So k value become infinity, 1 by k becomes 0. So in that case, what we write that q dash equal to minus q. This happens in terms of what? When you have conductors. You say it as conductors or you say it as metals. Okay, so in that cases, this will become equal. Both the charges will become equal. Okay, so this is what they have written for k is equal to infinity, q dash is equal to minus q, equal and opposite. Okay, next is Coulomb's force. We all know Coulomb's force is what? The first thing is the electrostatic force of attraction between two charges is directly proportional to the charge of the two product of the two charges and inversely proportional to the distance between them. If I'm assuming that these are point charges and between them the distance is equal to r, and this is what charge q1 and this is what is charge q2. If I join this two together, I get it as F is equal to k q1 upon q2 q1 q2 upon r square, where you get k value is equal to 1 by 4 pi epsilon naught, where so I write it as q1 of q2 upon r square. Now I'm talking about epsilon naught value. Epsilon naught is known as what? Epsilon naught is known as what? Permittivity. Permittivity of air. Okay, permittivity of air, whose value is equal to 8.85 into 10 raised to minus 12. For example, if this is an air, like this is, I'm trying to find this all, I'm talking about air or vacuum. This condition is for air and vacuum. Air or vacuum. Now, in case I want it to be in a medium, so for example, if I'm writing in the medium, so any medium, so I represent it with m. So I write that k is equal to, for this what I write, 1 by 4 pi epsilon naught in that medium, q1, q2 upon r square. We were trying to find out the ratio for this. So you can see that in the ratio, what we'll get it as? We'll get it as f naught by fm. We'll get it as epsilon naught by epsilon m by epsilon naught r, which is equal to epsilon r. This is what is the relation where we say that force of Coulombic force or force of attraction between the two charges are inversely proportional to the relative to the permittivity. And what is ER here? ER is equal to relative permittivity. Relative permittivity, and this relative permittivity only is known as basically your dielectric constant. Dielectric constant. Okay. Basic theories, no problem. So you have vector form again. This is superposition theorem. We'll see when we are doing the questions. What is basically if I want superposition theorem? So see, if I have two charges, I have a charge here as Q1 and I want to find its effect on Q1 and Q3. So Q2 and Q3. So what I'll try to find out effect of Q1 on Q2 and effect of Q1 on Q3. So what I'll try to write for that is I'll write it for that effect of K. So Q1, Q2 by whatever distance here, assume that this all is xx. So this is x square plus k q1 q3 upon x square, like that it will go on till how many charges you have. Okay, so they don't ask you what is superposition theorem, so only use for questions. Okay, now this is continuous charge distribution. We write it as linear charge density is linear word only. You can say it is per unit length. So charge per unit length, and surface charge density is basically charge per unit area. Again, you have volume charge density. The volume charge density is basically, we say what is it is volume upon charge upon volume. Okay, SI unit is Coulomb per meter because charge per unit length, charge per unit area, so Coulomb per meter square. Okay. Now, electric field we have to find out. To find out electric field, basically we have a formula F is equal to Q times E, or we can write that electric field is equal to F of 1 Q. Okay, or in this cases we write it as FQ naught, where Q naught is a test charge. Okay, So now where we are using electric field formulas, we'll see that if I want to find electric field, the electric field will be found out using, now say if I have two charges. So here see Q1 is there, or I'll take this as Q0 and this is Q. So if I'm trying to find out force between this, what I'll write, F is equal to K Q0 Q by R square. If I'm trying to find out electric field for this, F by Q will be basically this Q0 and this, if I'm assuming this is Q0, so this Q0 and Q0 gets cancelled, I'll get the answer as KQ by R square. Now why I'm writing this, both are vector. Electric field is also a vector, force is also a vector. So basically which charge will come? So because of this, okay, this will particularly create what? This will create a surrounding. This will create a surrounding. So in this surrounding, if any charges come, so what will be the effect of this particular charge on this one? How this Q0 will affect Q? This is what is electric field. Okay. So this test charge will what? It will try to do some, it will try to put some impact on this Q once it comes into the vicinity of that particular Q0 charge. Anyway, formula wise, this is what is the formula. F is equal to QE. We'll see another formula. F is equal to V by L. We have already seen it also in 10th grade. Okay, fine. So we'll come across this. So basically, if I'm talking about electric field is again voltage per unit length. This is again one more formula. Another formula is what? KQ by R square. Then this is also related as what? F by Q. Formulas in this chapter are important so that you can later understand this. Now, what is there? Electric dipole is basically you have two charges, plus Q minus Q. They are separated by a small distance. Okay, so that is small distance. I assumed it to be 2L. So this is what is known as what? Electric dipole, and the electric dipole moment is basically represented by P. It's a vector quantity which will be equal to the product of magnitude of either charge into the distance between them. Okay, this is what is the dipole moment. Unit, you can see the unit will be what? Coulomb meter. What is important here for this is that what a practical unit for this is what? It is dBA. Practical unit is dBA, not the SI unit. SI unit will be what? SI unit will be your Coulomb meter. Remember this. Coulomb meter is your SI unit. dBA is what? Practical unit. In practicals, what the unit is used for this is dBA. Okay. Now, for example, the next thing they're asking you to find out electric field intensity on axial line. Now, so find out electric field intensity because of an electric dipole. So what I'll do is first I'll draw an electric dipole. So electric dipole is there. You have a point A, you have a point B. You have charges here minus Q and plus Q. Okay. So on axial line, somewhere on the axial line, you're supposed to find out electric field because of assuming that here to here total distance is 2L. This one is L, this one is L. And what I'll assume that from center to here, from center to here, the distance is X. So when trying to find out answer for this electric field, first of all, this electric field, you have to find out the electric field here. It will be what? Normally the dipoles, dipole moment direction will be from minus Q to plus Q. So in case of axial line also, the resultant of this two will be there from the same direction, minus Q to plus Q. Remember, this is very important. Resultant of this thing. See, if I'm trying to find out, I'll assume a point charge over here. So if this is trying to put an electric field, so being positive, this will try to attract it on this side. And again, this is being positive, will try to repel it. So you can see that because of electric field, A will come here and electric field B also will come here. So this both will get added up. So if you try to find out the resultant electric field will come as 1 by 4 pi epsilon naught. K, okay, so P, so 2P. Okay. Or we'll write it in the short form so that we don't have to write all those things. KP, can remember it as resultant field. Here we will get it as Kp by 2Kp by RQ. 2Kp by RQ. Or here, if this is, they have written 2K RQ. What we have to write here is we have tried to define it. It will become 2K x cube. This is when it has shorter distance. You can prove it also, but it's like that much time is not needed to be wasted on here. And on axial line, it is 2 kp x cube. On equatorial line, if you are trying to find out on equatorial line, equatorial line will be what? It is like, say, if I have on somewhere here because of minus q and plus q. So for this E equatorial will be how much? It will be kp by r cube. It is x cube here. Where x cube is what? Is the distance between the center of the dipole to the point where the electric field is being calculated. Same thing here as well. Okay, now what is important here is when I'm talking about axial, the direction of the net electric field is not same in the direction of the dipole. But in case of equatorial, it will be ulta. Here in the direction is what? Here the direction of P is also like this. Electric field is also in this direction. But I'm talking about equatorial, the field, if the dipole is like this, electric field will be in this direction. This basically means 180 degree. Here it means 0 degree angle. You should know this. It's important. Okay, right? Now same thing electric field because of the equatorial thing. We don't have the this is what you can remember for your competitive part. This is what I'll write it here. Electric field, it is in general condition. In general condition, when you have a short dipole, we can write it as Kp by R cube root over 1 plus 3 cos square theta. Where now see if I'm talking about, I said if I'm talking about E axial, so E axial, that time this will become 0 degree. So if I'm writing 0 degree here, so this will become how much? Cos square 0 is 1, so 3 plus 1 4. 4 over root is basically it will give you 2 kp r cube. Like this only, substitute 90 degree for E axial, you'll get that. So you remember this value. This is the general value. This is true for short dipole. Short dipole. Okay, short dipole means where the distance between the dipoles can be neglected. Like this dipoles, this length can be neglected. So this is known as shorter dipole. Okay. Now the formula for torque when a dipole is field is like you have an electric field, uniform electric field. In this you place a dipole, so it will produce a torque. Okay. In this condition, for net force will be 0. F net will be 0 because one will give you plus QE, another will give you minus QE. So F net will be 0, but you'll have torque, and torque will be given by torque being a vector quantity is represented by scalar product of, vector product of electric field and dipole. So if you remove this, the cross product, you can write it as P sine theta, where what is theta? Theta is basically angle between, theta is basically angle between E and D. E and D. So if I'm writing the torque is equal to P sine theta. So if I have to find out that at what place T will be maximum, tau is basically what? It is basically in general, we're trying to define torque, it is what? It is the product of force into the perpendicular distance from the axis of rotation. So in this case, when it is put in a field, uniform electric field, that time the torque will be given as P sine theta. P here tau will be max when sine theta is maximum. Sine theta is maximum at sine 90. So that time it will be equal to PE. This will be PE when theta is 90 degree. When I'm trying to find out minimum, so tau will be minimum and sine theta is 0 degree because sine 0 degree is 0. So this is there when theta is 0 degree. Only if you remember the formula, that's enough. Okay, next is what we have is electrical force. The electric flux is basically because of now what happens, you have particular area. So you have a particular area whose area vector is represented by ds vector. So if on this there will be electric lines passing through this. So to calculate that how many electric field is passing to it, we have defined a quantity which is known as electric flux. Electric flux is given as electric field times ds. Electric vector times ds vector. Okay, or we can write it in the terms of E ds cos theta as well. where the angle is between E and ds. So E and ds, whatever angle is there. In this case, this is E and this is ds. So we try to imagine that here theta is equal to 0 because both are in the same direction. So this is what is your electric flux. Okay. So this is if the lines of force pass through a surface, it's said to be having flux linked with it. So how many number of lines are passing through an area, that is known as electric flux. Okay. Gauss theorem, the total flux linked with the closed surfaces 1 by epsilon naught times the charge enclosed by the closed surface. So total flux from an enclosed area, to represent enclosed area, we write it like this. Okay, so this will be equal to Q by epsilon naught, or you write it as Q 1 by epsilon naught, which is where Q is equal to Q enclosed you write, or Q inside you write. Okay, what is the from that surface, how much charge is there? That is what is your Gauss law. That is what is the Gauss law. Okay, this law is suitable for symmetrical charge distribution and valid for all vectors field obeying the square law, wherever you find out 1 by. Okay, so to solve the questions, what we try to do, we try to draw Gaussian surface around where we have to calculate the electric field. So it's an imaginary surface. It's a spherical for infinite sheet of charges, conducting and non-conducting spheres. It is cylindrical for infinite sheet of charge, conducting charge surface, infinite line of charge, cylindrical conductors, etc. This is just to write down that how we draw the Gaussian surface. Okay. So now this is application of Gauss law, which you have here. Electric, this is E is equal to lambda 2 pi r epsilon naught r. This is it's simple, like if I'm talking about infinitely long, so we take a long thing for a long infinite things, what we draw? We draw a cylindrical shape here, a cylindrical shape. This is basically a Gaussian surface. So imagine that the length for this was equal to this full r. Okay. This particular thing is length is L. Basically, from here we'll get it as so E is equal. We have no E dot ds is equal to Q naught epsilon naught. If you integrate here, you get it as E as E. The total area for this from where it is coming will be coming as 2 pi r 2 pi r L, which is equal to Q by epsilon naught. So you write E is equal to Q by L into 2 pi r E naught, and Q by L is we just write linear charge density, which is nothing but lambda. So we write it as this is what is the thing they are trying to say. Electric field due to uniformly charged thin spherical cell. If you have uniformly charged thin spherical cell, if you have a point which is outside, so say what we are trying to say is, if you have a cell have a radius of r. If you're trying to calculate electric field somewhere inside this, where or you can calculate it somewhere inside here or somewhere on the surface. So in this case, if I'm writing the case one will be what r is one is r is greater than r, other is r is equal to r, that is on the surface, and other is r is less than r. So for three conditions, we have the formula. So when r is greater than r, we have this is what is the formula kq by r square. If it is equal, it will become this. And if it is inside, it is 0. So inside thing, because there is no charge. All the charge, when I'm talking about something, some shell which is uniformly charged, all the charges will reside on the surface of the shell. It doesn't go inside. So if there is no charge inside the shell, there will be no electric field. On the surface, it will be kq. On the surface, it is kq r square. And when I'm talking about when r is greater, that time the radius will become here kq r square. Only that is the difference. This is the outside point here. This is on the surface. And here, anywhere inside that, you will be equal to. Using this, we have the graph over here. So it's basically 0 from here. Then r is equal to r, and then again it is like this because r square rectangular form. This is what this type of graph is basically known as what? Rectangular hyperbola, parabola. Next is again the same thing, uniformly charged non-conducting sphere. So that also three conditions are there. Okay, these are the three conditions. Electric field due to a uniformly charged infinite thin sheet is E is equal to sigma by 2 epsilon naught, where sigma is what? Q by A. Okay. Now we have to discuss about potential difference. The potential difference 1 point, like so from point A, this is point A, and this is point B. So potential difference is basically what work done in bringing a charge from one point to another point. That is what is basically a work done. Okay. If I'm telling only potential basically what we say, we are trying to bring a charge from infinity to that point. So some point A. So for this also you have to do work done. So like that only if I'm talking about potential difference, this is how it is given as potential difference is basically V minus VA. So if I'm trying to define electric potential, I'll define as a work done in bringing a charge from infinity to that point. If I'm trying to just write potential difference, is basically shifting a charge from one point to another point, or the amount of work done in shifting a charge from one point to another point. Okay, so electrical potential due to point charge, it is kq by r. Again, same thing when I'm talking about, so everything will be just divided by whatever you calculated there. So if I'm trying to calculate, say, E, E is basically, I have to find out whatever E value is there, you just divide that by R, so that will be your V value. If K, this was KQ by R square, this will become what? KQ into R. Because we just showed the formula E is equal to V by L or V by R. If I have to find out V value, V will be equal to E into E times R. So E value, if it is KQ by R square, so KQ by R square into R and R gets cancelled, so I get KQ. So if you find out, see, from finding out electric force, you can find out electric field. If you find out electric field, you can find out electric potential. All are connected to each other. Okay, as we said, we calculated electric field on axial line and on equatorial line. Like that only we can calculate the V also. For that, the common formula is this. Remember this, this is the common formula for this one. V is equal to Kp cos theta by r square. This is general formula. Here if you substitute theta is equal to 0, it's axial, 90 degrees equatorial. Okay, this is again same formula how I get calculated. Equipotential is that surface where when the work done in change, because they'll have the same potential. If I'm trying to write down work done, what is the formula for work done is we write work done formula is equal to Q VA VB or VB VA, whichever you want to write. Okay, VA minus VB. Now here what we say equipotential surfaces are those surfaces whose potential are same. If potential is same, that means difference will be zero. So difference will be zero, so Q into zero, so work done is zero. So for equipotential surfaces, potential is normally same. Equipotential and potential is normally same. The work done will become zero because it's Q times zero. So that's how we'll interrelate this. And this is what is the value for E with dV. Okay. Next topic is basically you need to know capacitance. Capacitance is C is equal to Q by V. Okay. SI unit is farad, millifarad is other thing, microfarad and picofarad. Capacitance is in scalar quantity. Dimensional formula of capacitance is m minus 1 l minus 1 t raised to 4 a square. You can write it by finding out the value for V. V is equal to electric field is V is equal to basically Q by R. So from there you can find out the formula for or the dimensional formula for this. Capacitance for spherical conductor is given by this, okay, where R will be the radius of the sphere. We will calculate that by using this only we have calculated the value also. Okay, so what is a capacitor? Capacitor is something which basically tries to store the charge. Okay, which is represented by this and this. This is constant. This is variable resistance, fixed resistance, and variable resistance. We have types of capacitor: parallel plate capacitor, cylindrical capacitor, and spherical capacitor. For this, we have formulas for this. For parallel plate capacitor, this is what is the formula. When there's air in between that, if you have some dielectric constant, we write it as K epsilon not A by D. Dielectric constant is basically some insulator if you're trying to keep it in between that. So capacitance will change. A is basically area of each plate, and D is a basically separation between the two plates. Okay, so you have this is what is then. From here to here it is D. One will have plus charge, other will have minus charge. This is how a capacitor will be. For that, when we are trying to, let's say what we did is, this is a capacitor between that to get what we're trying to insert a insulator whose thickness is T. For that, if I'm trying to write capacitance, capacitance will be given by E epsilon naught A D minus E1 minus 1 by K. This is when there is an insulator inserted in between the two parallel plates whose dielectric constant is K and thickness is T. Okay, so we can simplify this and write it as what C is equal to. Okay, why we have to simplify? For insulators, again, when we're talking about metals, K will become 0. Energy density formula, this is somewhere important. This is what is energy density formula, which is half epsilon naught E square, where E is electric field. Okay, sharing of charges. So common potential can be found out using this formula. And the loss of charges is found by using this formula. The formula will be basically loss of charges C1, C2, V1 minus Vt, basically half CV square. So we are writing that. So half is there, half CV square to C1 plus C2. This is for loss of charge in a capacitor. This formula is important. Loss of charge for a in a capacitor. Okay. So dielectric constant effect is this. When you're trying to, this is somewhere important a bit. When a dielectric slab of electric constant K is introduced between the plates of charged parallel plate and the charging battery remains connected. So they'll mention the question like the charging remains connected or not. If it is remaining connected, the new potential will be same. Okay, capacitance increases, charge on capacitor increases, electric field between the plates remains unchanged. So what is remaining unchanged, you have to remember that. And what is changing by how much, you have to remember that. This is when charging of the battery is remains connected. When dielectric slab of dielectric constant K is introduced between the parallel plates of charge Q, then charging battery is disconnected. That time how it will change. In that case, Q will stay same, capacitance will increase again Kc naught. Potential difference between the plates decreases by this value. Electric field between the plates decreases by this value. Energy stored in the capacitor decreases by this value. This is important in those two conditions. Okay, so this is the electric current which we're discussing, dq by dt. Now here you can see the formula is here. I is equal to Q upon T. Which they write it as NE upon T. Failures I is equal to dq by dt. Also can why we calculate it. dq by dt gives you some differentiation, which gives you some constant or some value, or which you try to find out electric. Now, still in the question, if they mention you that you need to find out the time where the direction of the current changes. Or in any case, I'm not only telling you the direction for this thing. Current. If you have any such situation where they're asking to find out that what is the time on which the direction for this particular changes. So for that thing, you have to just differentiate that equation and you have to equate it to zero. For example, if I have say Q is equal to that, which is that TQ minus 4t square plus 6, and they're telling you to find out the time where the direction of the charge flowing changes. So nothing you have to do, you have to just do dq by dt. So if you do dq by dt, it will give you 3t square minus 8t. If you get this thing, to find out the time where which the direction of this changes, so you have to take 3t square minus 8t, you have to equate it to 0. This will give the value for the time when the direction of the current changes. Dots. We'll come to the questions. I'm trying to do the theory faster only so that we can solve the questions. Okay, this is drift velocity. And drift velocity is basically what? When there's a motion of electrons, three electrons are moving. So there'll be what? One electron will be colliding to other. So during this thing, they'll have multiple collisions before they try to come to some stable position. So this is basically known as drift velocity. Okay. Before like electron starts from negative end and it tries to go to a positive end. So till here to here it will have multiple collisions. So we take average of all this velocity. This is what is known as a drift velocity, which is E. Again, E is capital E is electric field, M mass of electron. Tau is what here is relaxation time. Tau here is relaxation time. Now, what is the relaxation time? This is the time taken between the two successive collisions. One after another, both collisions before that will have some time. So that particular time is known as relaxation time. Now, so E is in the charge of the electron, M is the mass, E is the electric field applied, and tau is the time of relaxation. Negative sign shows the drift velocity of electrons is the direction opposite to the direction of external electric field. So it will they both will be opposite, and this electric field and E because of that. Now, what is the relationship between electric current and drift velocities? I is equal to NEAVD. NEAVD. Now, another term is there which is current density. So current density is defined as J is equal to I upon A. So I upon A basically will give it to us N E. Okay, now next term is mobility. Mobility is basically movement of electron, how easily it can move. So it is defined as VD upon E. If you substitute VD formula, you get it as Q E tau M E. After cancelling it, you get it as Q tau by M. Mobility is positive for both electrons and holes. It is not it's not a negative value. The units you can calculate the velocity by electric field. In case of current flowing through a metallic conductor of non-uniform cross-sectional, current is constant while current density, electric field and drift velocity are not constant. All vary inversely with the area of cross-section. Remember this. Current density, that is J, electric field E, drift velocity VD are not constant, all vary inversely with the area of cross section. Ohm's law, V is equal to IR, you know this. If some object follows Ohm's law, it is ohmic conductor. If it is not, it is non-ohmic conductor. So trying to keep the temperature constant, in that case, V is equal to IR. Okay. The slope of V and I will give you resistance. Now we can define, if I'm talking about resistivity, resistivity is directly, we write a formula which is equal to rho L by A. So this is what this basically says is resistance is directly proportional to length of the conductor, inversely proportional to the area. It is dependent on the nature as well as temperature. But when I'm talking about resistivity, resistivity only depends on the nature of material. Nature of material. Resistivity doesn't depend on the value of length or area. If material changes, or the value for resistivity changes. Okay, and there is a term conductivity. Conductivity is in physics we write it as sigma. Sigma is basically 1 by r. The conductivity is reciprocal. Conductance. This is conductance. So conductance is reciprocal of resistance. Also, when I'm talking about resistivity, it is the inversely of resistivity is basically conductivity. This is small things which is about in which we wrote the Ohm's law. Ohm's law is can be written in the vector form as in this. J is current density, sigma is conductance into E. This is Ohm's law in vector form. Anyway, this is few formulas which you already know. Now you know this Vd is equal to E V tau by ml. No, we just substituted the formula for E. E is nothing but V upon L. So electric field starts flowing through the conductor by time. So these are few formulas where I is this. Then V by I is basically equal to R. And this rho L by is basically the resistance. Rho L by is basically resistance. Same thing, free conductance G is equal to 1 by R. We write it as this. Conductivity sigma. The electric energy, again, obviously energy is important, but you know that it's free energy, power of doing work is what basically we're talking about. I'm talking about power. The power is equal to rate of doing work. So here we write it as when I'm trying to find out electrical energy is P into time, because energy and work have basically same meaning. So power into time. So that's why using this only we try to calculate kilowatt hour or watt hour, whatever the unit is. Normally kilowatt hour, 1 kilowatt hour is considered to be 1 unit. And if we are talking about the electricity bills, normally we get another one. Now resistors in series, parallel and series, you have to see resistance in parallel. The equivalent resistance is given as R1 plus R2 plus R3. And in parallel, it is written as what? 1 by R1 plus 1 by R2 plus 1 by R3. It's a small difference in that, nothing else. What is there basically in this, like how I write this in talk, if I'm talking about this is condition of series. When I'm talking about series, what is constant? Current is same. When I'm talking about parallel, so this is basically for parallel. In parallel, what is there? Voltage is same. So using that, we try to derive this. Okay, so electric motive force, small definition, it is defined as the potential difference between two terminals of cell in an open circuit. That is when no current flows to the cell. Okay, when no current is flowing to the cell, that time whatever potential difference will be there, that have that is known as electromotive force. Okay. Like that only we have terminal potential difference and internal resistance of the cell. Kirchhoff's law obviously is kind of important. We'll see that when we are trying to do numericals. We would have done it already. So we have two laws for Kirchhoff's. One is current law, and the other one is voltage law, which we say it as KCL and KVL. KCL and KVL, two particular type of Kirchhoff's laws there. Okay, so the first law says is this is the junction. So how many you have this, okay, this from here current is coming, from here current is coming, from here current is coming, from here current is leaving. So number of current leaving or coming to a junction, we write it together. So that's what is your current law. It states that the algebraic sum of the currents meeting at a junction is equal to 0, it follows conservation of charge. And when I'm talking about second law, that is KVL, it states that in a closed loop, algebraic sum of EMF is equal to the algebraic sum of products of resistance and respective current flowing through them. Okay, so it's equal to E is equal to IR. It is basically instead of V, we are taking the condition of EMF, where you were trying to say electromotive force, because electromotive force basically consider one that electron flowing through that time when you're talking about this electromagnetic force. Electromotive force, that time current when drawn is maximum through it. Okay, Wheatstone bridge. Wheatstone bridge is basically, I've given you the equations here. What happens here is, this is what you have to know. PQ by is equal to RS. The P and Q is upon the ratio of P upon Q is equal to ratio of R upon S. This is how we write this thing. This is what is basically a Wheatstone bridge. This is a Wheatstone bridge. And when I'm saying that, when the ratio of this thing, either you write like in condition if P by Q becomes equal to RS, so in that condition, there will be no current flowing through this particular VD. So there will be no current detected by galvanometer. This is galvanometer G, so there will be no particular current which will be going, which will be flowing to this particular arm. That's what is sweet. So either way, it is there. If you have, like, if there is no current flowing through G, we can write that ratio of P by Q will be equal to ratio of R by S. And if in ulta you want to write, if P by Q is equal to R by S, then in that case, there will be no current flowing to the R BD. So either case, it is same thing. Okay. Next is potentiometer. Potentiometer is basically what we try to do in potentiometer. It's based on the fact that the fall of potential across any portion of wire is directly proportional to its length of that portion, provided the wire is of uniform area of cross section. Okay, so they both will be proportional. Wherever there will be a fall in potential, there will be a particular length, and it will be proportional to that particular length. Okay, so this is basically comparing the EMF of two cells using potentiometer, we write. So ratio of this is equal to this. So basically E is equal to directly proportional to it. Also, to find out the internal resistance R, we can use this by taking L1 minus L2 upon L2 into capital R. The formula is the formula. R is equal to L1 minus L2 upon, this one is L2. L1 minus L2 upon L2 into R. This is ratio of one EMF to the other. So basically from here what we can write, E is proportional to L, which we written in the previous, E is proportional to L. Using this, we try to calculate the, we can compare the EMF for two cells. So the length and this length is given, one EMF is given, we can find out another EMF. Or we can find a ratio. To find out the ratio of E1 by E2, we just calculate L1 by L2 from experiment, and that what will be the ratio of E1 to E2. So what is ammeter? Ammeter is an instrument. Ammeter is what's an instrument to measure current in an electrical circuit. Like this only we have said, we have galvanometer. When we're talking about galvanometer, is again same thing. Galvanometer is used to measure current itself, and it can be also changed. One particular switch is changed in that, starts behaving voltmeter. So galvanometer is more sensitive compared to ammeter. Like if you're talking about comparison between ammeter and voltmeter, we say that as a 10th grade student, we have studied is that it is, when I'm talking about V, it is potential. And when we're trying to compare this with galvanometer and ammeter, so basically what we try to do is ammeter and voltmeter, ammeter is always connected in series to the circuit, and voltmeter is always connected in parallel to the circuit. Ammeter is what? It have lesser resistance when it is compared to voltmeter. And comparably, the ammeter have lesser resistance compared to voltmeter. So what we do, we have to, as we said that it is always connected in series, what we do is ammeter is used to, what we did, we took galvanometer and converted into ammeter. To convert galvanometer into an ammeter, what we do is, it's just normally what we do is we take an ammeter of given range by connecting a suitable row resistance S, which is known as called shunt, in parallel. Okay, when you're going to convert galvanometer into ammeter, what you have to do is we have to just take a low resistance. See, we have to take low resistance. Okay, which is known as low resistance is known as shunt, and that shunt have been connected in parallel. Okay, this is what is shunt resistance. S is equal to IG. This is IG. This is IG upon I minus IG times G, capital G, which is what G is here. The value for this is I minus IG, and this is IG value. Okay, ammeter is a low resistance instrument and it has always connected in series to circuit. An ideal ammeter has zero resistance. Now next is voltmeter. For voltmeter also same thing we try to read. The voltmeter is what? Voltmeter, to convert voltmeter, what we do, we take again same thing, we take suitable resistance R in series with galvanometer. There it was what? Suitable resistance S, we are trying, that is shunt, we are trying to connect that into parallel. So here it is series, R is equal to V by Ig minus capital G. Okay. Again, voltmeter is high resistance instrument. It is always connected in parallel with the circuit diagram. Okay. So voltmeter is a high resistance thing, ammeter is a less resistive thing. While we are changing the things, if I want to substitute it, this is how we can use which one you want to substitute from which. Now voltmeter is what? It's a high resistance instrument. Ammeter is low resistance. It's always connected in parallel. Ammeter is always connected in series. So differences you have to remember. Okay, an ideal voltmeter has an infinite resistance. In order to increase the range of an ammeter n times, the value of shunt resistance to be connected in parallel is this much. This is what if you're trying to increase the order of range for n times. Similarly, if I'm trying to do it for your voltmeter, it will be basically R is equal to n minus 1 into G. Galvanometer, n minus 1. Okay, so this is some basic theories from electricity chapter. Let's try to do the questions. Okay, this is the first question we have. We all can try doing it. We start on doing it. If we are done with this number of questions, we can move on to further. I have 10 questions at present. It's there, 10 questions are there in slide. If you're done with this 10 questions, we can go further. I have uh, n number of questions, so that's not an issue. So we'll start with this thing. Just a brief revision of the formula. That's all. Try this. Yes, answers and solve. I have some answer. 0.1 second. Okay, let's solve. So now they are saying what is we have 10 raised to 12 alpha particles. So alpha particle is basically we write helium 2 4 per second falls on a neutral sphere. Okay, so it is falling on a neutral sphere. Find a time in which the sphere gets charged by 2 microcoulomb. So the total charge they have given you is 2 microcoulomb. Charge Q is 2 microcoulomb. This is first thing I have. Now they're telling me to find the time. Okay. So I know that Q is equal to basically, I know Q formula is equal to N times E. Now, if I'm trying to find out N, I have this much 10 raised to 12 alpha particles in per second. So in 1 second, I have basically 10 raised to 12. So imagine for 10 second, it will become 10 raised to 12 times. So the charge, it will become 10 raised to 12 times T will be N value. Now you can see if I'm talking about an helium atom, this is what is the charge. Okay, so charge here will become 2E. Okay, this is, and the Q what they have given is 2 into 10 raised to minus 6. I hope this is clear. So if I'm trying to find out T value, so this 2 and 2 gets cancelled. T is equal to, basically I will write what, 10 raised to, so minus 18. So I can write 10 raised to minus 18. Coulomb, this is 1.6 into 10 raised to minus 19, right? So we just remove this 10, 16, 100. I think something around 100 by 16. So something 6.25 something. So 6.25 seconds. Okay. Because I have written 2 raised to 12 alpha particles per second. So it was 1 second, it is 10 raised to 12. So I had to find the time in which sphere gets charged this much. So I assume that for that time was T. So for that total number of this will be this much. N. This is N value. The substituted N is equal to, this is what we are using. We are using quantization of charge. I hope it is clear. Okay. Let's go to the next question. Next question is this. Electric force between 2 points, this at rest is F. Now if the charge minus Q is placed next to Q1, what will the force on Q2 and total force on Q2? Okay. This thing, if that, this is basically they're asking the electric force. Electric force between 2-point charges Q1 and Q2 are at rest is F. Basically, first what was there? F is equal to KQ1 Q2 by assume distances are so r square. Now if the charge minus q is placed next to q1, this was q1, this is q2, q1 and q2. So in between this, if you're trying to bring charge next to q1, it can be this side or this side anytime. Putting it here. So what will be the force on q2? How the force on q2 will get affected? Force, we are talking about force thing, force, how it is trying to affect this. This is negative charge, and this the charge they have not mentioned, so we'll assume this as positive. Okay, so what we write basically right now, if I'm writing F is equal to that, F is dependent on it is either dependent on Q1, Q2, or this is dependent on R square, basically distance between them. So I say if you bring any charge Q in, this it will not put any effect on the force. Electric field might change because the position of Q1 will change, but force will not. So the thing is, electric force is not affected by, it is independent of presence or absence of any other particle. It is only dependent on the charge between which it is there. The total force you can calculate by using what? By using the formula. For this one you can find out. For this, because of this you can find out on this. Because of this you can find out this. So for Q2 it will try to attract it on this side. Q1 will repel Q2. So this both is in the same, in opposite direction. I'm assuming that if their magnitude is same, in that case the net force will be equal to 0. If in case the magnitude is not 0, so I can't find the value because the data will be insufficient. Because of minus q, if I write F because of minus q, I write it, if there will be some distance here also, this is x, and from here to x this will be equal to, this is r. So I write F because of minus q will be what? K q into q2 upon x plus r whole square, if the magnitude is not same in that case. And F because of q1, it will be k q1 q2 by r square. So because we have to use this 2 to find out the resultant. But in case if the magnitude is same, that time total force will become equal to 0, because one will be trying to pull q2 towards itself because of its negative charge, and one because of its positive charge will try to repel q2. Okay, third question. Try this. For system listing, find Q for which the resultant force on Q is 0. Okay. Resultant force on Q. Talking about this one. this is also A. It's basically a square, so all sides has to be A. Q upon square root of 2. And bottom I have answer Q upon square root of 2. This is FA and this is again FA. So if I find resultant of this two, this will come on this direction, right? Angle between them is 90 degree. So using vector, basically I can find out this. Using vector, if I'm trying to find out vector for this two, this FA. So I write it as what? FA square plus FA square plus 2 times FA into FA. Cos 90 degrees. So as cos 90 degrees, this is what is the resultant of this 2FA. This is under root. So cos 90 is 0, so this value is 0. So this will become root 2 FA. So resultant. So here this will become root 2 FA. After this is root 2 FA. So now basically I can write that root 2 FA will be equal to FR. Now FA value will be how much? FA will be equal to K capital Q small q upon what will be the distance over here as A square. For this particular charge, if I want to write, I'll write it as K Q into Q upon distance from here to here will be what? This will be the diagonal of square. So diagonal of square is basically root 2 A whole square. I hope you know how to find the square of this using Pythagoras theorem. So this is A, this is A, so this will be root 2A. Okay, A square plus A square under root. If I solve this and this gets cancelled, K gets cancelled. So basically I'm getting what? I'm getting root 2 on A square, root 2Q upon A square equals to Q upon 2A square. So again, A and A square also get cancelled. So we are getting it as a relation. If you write small q is equal to 2 root 2 capital Q. 2 root 2 capital Q. So Q upon square root of 2. That means your answer is this. Q is equal to, it should be this one. So what is the question solution? I hope I'm clear. Let's go to the next question. Next question is two positive point charge. This thing is separated in vacuum by distance 3 meter. Find out. Yeah, you will get the PDFs once the classes are done. And so 1 meter from 4 microcoulomb. 1 meter from 4 microcoulomb. Yeah. So for example, if I have a situation, this is what is, and imagine that this is what is Q1 here over, and this is Q2, and so this is 4 microcoulomb. 4 microcoulomb. This is 16 microcoulomb. Total distance given to us is 3 meter. So what is 3 meter? So what will assume that I will assume the point somewhere in between, and we will try to put it more closer towards Q2 point. Reason is because if you talk, this is 4 and this is 16, so this is having more magnitude when I'm talking about comparing Q2 and Q1. So we should try to put this P closer to this Q2 so that the smaller charge will can balance the field because of the larger charge, because it will get more distance. So because of increase in distance, it will have more electric field which can be balanced. So we'll try to put the P nearer to Q2. Let's see that. So they both should be in opposite direction. It will be in opposite direction. Why? Because I'm assuming this as a point charge. They have not mentioned the charge, so we'll assume this is a point charge positive. So one will put it in this direction. And we have to find out at a point where it will be net electric field is zero. Net electric field will be only zero if they are both are equal in opposite direction. So E1 is there. So in this K and K will get cancelled. KQ. So if I write what it, I'll write it as K1, KQ1, R1 square equal to KQ2 by R2 square. KK gets cancelled. Q1 by Q2 we have. So I can write that R1 by R2 can be written as root over Q1 upon Q2. So Q1 is basically 16 microcoulomb and this is 4. So root over this, so root over of 4, I get it as equal to 2. So R1 by R2 is equal to 2. Also, we are given with this R1 plus R2 is equal to 3. So using this, if I'm writing, I can write that R1 is equal to basically 2R2. So 2R2 plus R2 equal to 3. So R2 is equal to 1 meter. I can write either from R1 2 meter or from R2 1 meter. So his answer was right. Just give you an answer for this. I hope it is clear. Will you go to the next question? Yeah. So an electric dipole is placed at the center of sphere. Find the electric flux passing through the sphere. Passing through the sphere. See, they're talking about the electric flux. The formula for electric flux is basically this EDS, which is equal to Q by epsilon naught according to Gauss theorem. That Q here is basically the Q enclosed or Q inside. When we are talking about the sphere, and if I'm talking about the center, we have just read that Q in is zero. That's why electric flux also is zero, which is equal to by phi. Phi is zero. Why phi is zero? Because Q inside the sphere is also equal to zero. Okay. We just read that electric flux for the sphere condition, it will be KQ by R square at surface. It will be KQ by R square when the point is outside the sphere, and inside the sphere it will be zero because all the charge will be residing on the surface of the sphere. There's no charge inside this. That's why it is equal to zero. The electric field is also equal to zero. Okay, next question. The electric potential at point A is 20 volt and at B is negative 40 volt. Find the work done by the external force and electrostatic force in moving an electron slowly from B to A. Okay. See, as the definition of electric potential says that you have to bring a charge, the work done in bringing a charge from one particular point to another. Here we have to bring it B to A. So if I have A and B, I have a charge Q at B, I'm supposed to bring it at A. So work done in bringing a charge from one point to another point. So find a delta V. So final minus initial potential, VA minus VB. Now, Q is given as, we have any Q over here? Okay, an electron is that, fine. So an electron is basically 1.6 into 10 raised to minus 19 Coulomb the charge. VA potential at A is 20 minus potential at B is 40. So this is 1.6 into 10 raised to minus 19. And we have another 20 plus 60. So 6 times 6 is 96. So 100. So 9.6 into 9.6 times. So that's the minus 18 joule. Because I'm trying to bring an electron, so I'll use the charge of electron. It will be basically this much amount of water. I'm trying to do this is what we are trying to find out work done by the external force. This will be the work done by external force. If I have to find out the work done by electrostatic force, it will be just negative of this, negative of, find out electrostatic force, whatever we get here, as that will be, same thing will be negative of what you get it as work external, because both will be acting in ulta direction of each other. So this will become positive, 10 raised to minus 18 joule. Okay. Please go through this. If you have doubts, you can ask. If not, I'm moving to next question. You have to try to do more and more questions. That's what is my focus. Physics without questions. These are scoring chapters. Okay, we have some capacitor here. You can do this. These are still basic questions. Okay. Which direct formula based questions type or small concept type. So we do this and then we are going to the vacuums. So the question is, yeah. Gautam says 96 PF picofarad, right? Others, please try. If you have exams, I think you're already knowing the basic formulas to substitute. This is basic formula, man. If you're talking about this thing, this question basically says it. What if I'm talking about, because it's air capacitance, I can denote it as C naught for my convenience. So the formula for this is epsilon naught A upon D, which is given to you as at 8 picofarad. What they're saying that it is distance between the plates is half, and there is some dielectric constant of 6 is placed. So if I'm playing dielectric constant, this is C medium. So for dielectric medium, we multiply Q, epsilon naught A. The distance between them is half. So this is basically, it will become 6 into epsilon naught A upon D times 2. Basically, it is 12 times. This is nothing but equal to C naught. This value is C naught. So 12 times C naught. 12 times C naught will be 12 times 8, which is equal to 96. Okay, cylindrical capacitor has to, it's I think this is not important. Yeah, we can do this. Good question, lazy question. I feel it is lazy, but maybe you all can do it faster. This is a battery, 300-volt battery, positive, negative side. Equivalent capacitance is 300 Faraday. Correct. Equivalent capacitance. So parallel. This is C4. This is C4. No, equivalent capacitance, how it will be 300? It will not be 300. No. 100, 200 and 200 for this in series, so that will become 100. And then two, either you can take all three is, oh, you're taking all three as parallel because of that. Anyone else have answer? Determine the charge and voltage across each capacitor. Everyone have at least the equivalent capacitance answers. You have 300. Got them equivalent capacitance. Is it 300? It is something different. No, Suyong, it's not. You have not done mistake. I just want to know if others are getting same answers or not. Because if you got that answer, then it is same thing everywhere. And this much long question you will not get. Just to brush up your concept, you can use these things. Okay, so fine. Try this. Then we'll go to PYQs. This is again formula. So in this chapters, you can directly expect most of the questions will be formula based. Few will be small concepts. Small concepts. They'll not give you calculations, big calculations from this chapter. They'll give you calculations also in that way so that it will get cancelled. Try this. How much is the electrostatic energy is stored by the capacitor? So energy is stored, you have to find out. View this energy is stored in the electrostatic equilibrium and obtain the energy per unit volume. Hence arrive at a relationship between U and the magnitude of electric field E between the plates. Okay. Okay, you have to find out electrostatic energy which is stored in this. So you can use the formula C is equal to epsilon naught A upon D to find out capacitance. So it would be equal to what? 8.85 into 10 is to minus 12 into area is 19 to 10 is to minus 4 upon the D is equal to 2.5 into 10 is to minus 3. So 8.85 into 10 is to minus 3. Okay. So it is giving you the answer is 32 microfarad. 10 raised to minus 12. 10 raised to minus 12 is a picofarad. Okay, it will give you as picofarad. The picofarad is, so I know the formula for this is what? It is equal to half CV square. So this will be equal to what? Half C is 32 into 10 raised to minus 12 to convert it into SI unit Faraday. V square is 400. So square of 400. So basically 16, 464 and 4. So 256. Okay, so 2.56 00 so 4 minus 6 2.56 2.56 into 10 raised to minus 6. Yeah, right. Same answers. 2.56 10 raised to minus 6. So I'll write it as micro. What I have to find out energy, so joules. Okay. Now they're telling you view this energy is stored in the electrostatic field between the plates and obtain the energy per unit volume. Okay, I have to calculate energy per unit volume. So say I have U is equal to half CV square. Now if I'm substituting C value is epsilon naught A upon D, and as E is equal to V by L, I can write V is equal to E times L, where here it is equal to D. So it is basically E square and D square. So I can cancel one D to D here. So finally, when I'm trying to, now they're asking you to obtain energy per unit volume. So to find out per unit volume, so this is energy. I know I can write area into distance as volume. So per unit volume, this one becomes, I have half here, then epsilon naught and E square. So this is what will be the, remember this as well. This is energy per unit volume. This is an important formula which can be used for few questions. Let's try some IQs. So what are those? The question says is, the first question we can do. So you have the point charges, you have 2 point charges, Q and minus 2Q. 2 point charges are there. They have some distance, we don't know. Okay. They have some distance between them, which we don't know. If the electric field at a location of Q is E, here the electric field is equal to capital E. Okay, the electric field at the location of Q is E. The electric field at minus 2Q will be what? You have to find out electrical field value over here. Okay, I don't know what is the distance. They have given you two charges which is separated, the Q and minus 2Q are separated by some distance. The electric field at capital Q is equal to E. So you have to find out what will be the electric field at location minus 2Q. That's what is your question. Yes, you can go ahead with it. Answer 2 times of E. Think once. Actually, the thing, your thought is fine. Now, see, if I'm trying to use this relation, so at this place, if I'm trying to find out force, force will be equal to QE. And this particular force is being applied on this charge as well. So at this particular place, F will be equal to Q, this particular charge, this will be applied again. So the force will be basically what it will be there. One side it will be going in this F, this one, and one side because of this it will be putting the force. So basically what I write at this point, this particular force will be having the same magnitude. But what will happen here, as here F is equal to QE, but in this case electric field will become what? So in this case this will become 2QE. So electric field will become F by 2Q, where F in the first case we got it as QE. So assume that it is E dash over here. So E dash will become F by 2Q, which will be QE upon 2Q. So this gets cancelled. So it will be E upon 2. Logically also, if I'm talking if the charge is increasing, so in that case we are supposed to maintain it, and it is negative 2Q. So obviously the E have to decrease so that it can maintain the charge. F is equal to Q at the first position. Using that, we can find out this. Next question is this. We have a plus Q charge here. We have a minus Q charge here. And we have a plus Q charge here. This is the system. This is the distribution of charge. For this, we have to find out the electric flux due to this charges to the surface S. This is surface S, and to this we have to find out the electric charges, the electric flux because of these three charges. Options are 3q epsilon naught. Second option is 2q epsilon naught. C is q epsilon naught. D is 0. The question is, what is the electric field inside this? Gautam have an answer, right? Because see, inside every conductor, you don't have to think only. Inside means it will be equal to 0. You don't have to think about anything else in that scenario. If they're asking you the question that inside the conductor, it is what? The flux electric field through this charges through the surface S. If the here the electric field will be inside situation, outside I don't have to care about, inside will be 0. Okay. Okay, we have another question is we have two parallel thin sheets, metal sheets. We have two metal sheets. Okay, so two metal sheets. This both have sigma surface charge density. Sigma is surface charge density is 26.4 10 to minus 12 Coulomb per meter square. Okay, they have opposite signs. So if one is plus sigma, other one is minus sigma. You need to find out electric field between this sheets. Electric field between this sheets. Okay, so what is the question? So when I'm talking about one sheet, so for one particular sheet, the electric field is given as sigma 2 epsilon naught because I have to find out in between. So it will be addition of both of them with the opposite sign between them. So for that, the formula will become, Sunil says it as 3. I think you're right, 8.8. Yeah, you're right, yes. So the answer for this is basically to find out the electric field here, it will be sigma epsilon naught. So sigma is 26.4 into 10 raised to minus 12 Coulomb meter square. Epsilon naught is 8.85 into 10 raised to minus 12. So approximately, if you cancel this, it will come with us 3. So this is what it will be approximately equal to. Okay. This is basically how the questions will be. Obviously, this is not enough. To try one more question here. Just one more. Okay. So what is the question is the potential at a point P due to an electric dipole. So I have a dipole here. So minus Q and plus Q. Okay. So there is a point P here, which is at a distance of 50 centimeter from the center O. So this is center O. The point P, distance from here to here, it is 50 centimeter. Okay. So electric dipole is given to you. The electric dipole value is, I'll write it here only. Electric dipole value is equal to 1.8 into 10 raised to 5 volt. This is given to you from center for if CP makes an angle 60 degree with the positive side of the axial line. So we have CP is there. This is the that will make an angle CP. This is what is you're trying to say. There's an angle 60 degrees being made over here. Theta is 60 degree. So what is the moment of the dipole? See, for finding your potential, well, the formula is what? AP cos theta by r square. Directly general formulas we have to use in this cases. This is what is the question here. Potential is given to you. So the formula for this cases are what? We have to find out electricity, the electric field, it is what? K P by R cube root under 1 plus 3 cos square theta. For finding out potential thing, what we do, we write it as Kp cos theta R square, where R is the distance between the distance from the center to the point where we are supposed to calculate the electric field. So if we have to find out the value for, we can substitute this thing is given, the potential is given is 1.8 into 10 raised to 5 volts. Okay, we have to find out the electric dipole. This is V. Potential is given to you. So we have to find out 1.85 into 10. We have K values 10 raised to 9. Then we have to find out P. So P will stay P cos 60 degree. R square is basically what? 50. So 50 into 10 raised to minus 4 meter. So we have to calculate P. So P will be something 1.8 into 10 raised to 5 into 50. Okay, so I can write it as if this is cancels cos 60. So I can write it as 0.25 into 2 upon 9 into 10 raised to 9. So this will give you answer something around 10 raised to minus 5 Coulomb meter. So this general formula for potential thing and for electric field, it is what? It is Kp R cube root over 1 plus cos square theta. Please remember this. Cos square theta. Okay. No, Shreya, you maybe you would have tried solving and the questions would have been tough because you would have tried directly this thing without some. See, they try to manage the averageness of the question. If one topic will be hard, so other will be easy. It's not that everything will be hard. They have to keep in mind that it could be solved in this prescribed time. So you might would have solved one model paper with that model paper and that particular one Those chapters will be hard, which you would have not read full, or maybe you would have not practiced. But electrostatics things, these questions are easy questions, you feel, but it is formula based questions. These are basic questions. But further, when it comes to practice, maybe in some topic you can get high level questions, but that doesn't mean that this kind of question doesn't, it's not asked. This kind of questions are also being asked. Okay, so don't worry, just keep on practicing. Don't uh, depend or don't just be like disheartened with your practicing model test papers. You might get easier questions. Model test paper, usually we, whatever we see or whatever we prepare, we try to keep it on the higher side so that students practice a higher level set of questions. So please don't worry about all that. Just keep on practicing, keep on studying. Okay, fine. Thank you. We'll end the class today here. Yeah.